From last lecture, we have discussed a lot of concepts, which is quite new for a lot of people. So here I'd like to use this first slide to summarize what we have discussed from the last lecture. First, we understand that there's a system, surroundings, and a universe, and each system or surrounding or universe has their own energy. And according to the first law of thermodynamics, we understand the energy change of the universe, which is delta E of the universe, is equal to 0. So that leaves us the delta E of the system equals to the negative delta E of the surrounding, which means the energy change of the system has the opposite energy flow with the energy change of the surroundings. So the negative sign here is very important because the negative sign tells us what direction of energy flow is if we want to compare this against to something else. Second, I'd like to point out that if we talk about the energy change of the system, there are two ways to have this energy transfer. One is heat, one is work. Speaking of heat, Q is equal to C times M times delta T, which is we call heat equation. And C is the specific heat, M stands for mass, delta T means temperature difference. What I'd like to point out here is that delta T, the temperature difference in Kelvin, is equal to exactly the same value of temperature change in Celsius. So there's no need for us to add 273.15 to the temperature in order to convert Celsius to the Kelvin. There's no need. As we already explained, there are only two energy transfers. One is heat, one is work. So if we have to think about the energy change of a system or the energy change of the surrounding, delta E is equal to Q plus W. So these actually contains three different equations, right? So delta E system equals Q plus W. And from that equation, we need to know exactly what sign that we should assign to heat and W from the perspective of the system. And heat equation tells us just how we're going to calculate heat. And that's just something we need to know about the delta T as the temperature change. Speaking of the directionality of energy flow from the perspective of the system, work should be considered as a plus value if work is done on a system. In other words, system accepts work. If we have a work that's done by the system, that means the system exports work, or system does the work. In other words, system losing energy by doing such work. Speaking of heat, same logic. Plus, when system gains energy, gains heat. Of course, this gains can be replaced by many other words like absorbs, so on and so forth. The system loses heat is where we start to assign negative sign in front of the value. The word of lose can be replaced by evolves, releases, so on and so forth. So here, it is very important for us to understand the sign of the energy before we conduct any other calculation or try to answer the question. If the question has already predicted the direction of the energy flow, we do not have to mention the sign unless we have different opinion. The last section of our last lecture is the state function. State function is a very important concept in thermodynamics. The state function tells us this is the function that only depends on the state. Or sometimes it depends on two states. One is final state, one is initial state. Nevertheless, state function is very much independent of the path the system chooses. So regardless of how the system chooses the path, that value remains the same as long as those two states or the state does not change. With the understanding of the state function, a new energy term has been defined. We call it H, which is the enthalpy. What is more important about this enthalpy is when we talk about change in enthalpy, it can be measured by the heat under the constant external pressure. This is the milestone of the thermodynamics because we cannot measure directly to any state functions that easy. However, heat is something that we can measure because we already have the heat equation. So we can use the heat we measure under certain condition and replace that for the delta H. And delta H is a state function. Delta H can use that value for some other conditions or some other reactions and so forth, which we will see that in today's lecture. Before we left our last lecture, we talked about the types of chemical reactions. So there are two types of chemical reactions. One is exothermic, one is endothermic. For exothermic reaction, delta H must be negative. So the heat of the reaction, the enthalpy change of the reaction, delta TH reaction, they're all the same, must be less than 0. If energy, the system has the energy that's less than 0, meaning that the system loses energy by reducing heat. So heat coming out of the reaction, so that's why we call it exo. Endo is the opposite. During the explanation of exothermic and endothermic reaction by using the same equation, the only thing is we change the direction of the arrow. So we realize that if we want to reverse the reaction, we have to change the sign of the heat of the reaction. This is one of the important maneuver that we're going to see later on when we talk about Hess's law. Now, let's talk about chemical reactions focusing on the delta H. From our last lecture, we understand that if we have hydrogen react with oxygen to form water, this reaction generates a lot of heat. How do we know it generates a lot of heat? Because delta H of the reaction is negative. Meaning the system, also known as reaction, loses heat. Heat is coming out of the reaction. The delta H of the reaction usually has the unit of kilojoules. However, if we have a delta H of the reaction that's associated to the reaction, like the one that we have right here, I would like you guys to realize this is kilojoules per mole of such a reaction taking place. Why is that so important? Because that actually can be used as a conversion factor because we have kilojoules, moles, they have two different units. Not even mention the units come from two different dimensions. If we combine the equation and the heat of a reaction altogether, we call it thermochemical equation. This is a balanced chemical equation including the states of the substances and heat of the reaction altogether. We're going to talk about the stoichiometry about this delta H of the reaction and the reaction itself in our next slides. But here, I'd like to let you guys to realize there's some manipulation of the reaction. First, from the previous lecture, we understand If you reverse the reaction, we change the sign of a delta H reaction. What used to be the exothermic reaction now becomes endothermic. As a matter of fact, if we want to pick a hydrogen as our next generation of fuel to support our society or humanity, how to decompose water by using energy, which is come from a very cheap way, is the most challenging that we have to face, especially to the scientists. Because as we can see here, that is a positive almost 600 kilojoules per mole of such a reaction, which means in order to get only 4 grams of hydrogen, we need to put in almost 6 kilojoules to get it. So still, how to utilize the energy that is very cheap to get this hydrogen collected is the biggest challenge that we have so far. If we want to use hydrogen to support our society. But that is a little bit over our topic here, our head. But when we look at these two reactions, we realize if we reverse the reaction, delta H of the reaction has a sign change. Therefore, the first manipulation for thermochemical equation is, if a reaction is reversed, we change the sign of the delta H of the reaction. Second, we're going to focus on the magnitude of this heat of a reaction. Say we have a thermochemical equation that's been laid out. So it requires 2 moles of hydrogen and 1 mole of oxygen to yield 2 moles of water. Such a reaction will give up 572 kilojoules. However, for the same equation, this time we only use 1 mole of hydrogen. So now that we cut down the amount of hydrogen from 2 moles to 1 mole, how much heat do we expect? Of course, we have to cut down heat by half as well. So from this calculation and the discussion that we have, we realize that heat of a reaction is also depend on the coefficients of the reaction that we pick. So here comes our second manipulation on the thermochemical equation. If we double the reaction, we double the heat. Of course, you can also say if we have the reaction, we have the heat. Third point I'd like to make here is pay special attention to the state of the matter. So for example, if water is a liquid, it gives up 572 kilojoules. If the water is not a liquid as a product, but gases or steam, you see there's a quite different value here. Quite less, right? It's only negative 484 kilojoules. Pay good attention to the states of these substances, because different states wants a different amount of heat. Two things I'd like you guys to pay special attention when we talk about manipulation of a thermochemical equation. First, change the sign when reaction is reversed. Second, double the reaction, we double the heat. These are the two major manipulation when we deal with one of the toughest topic in this chapter, which is Hess's law, which we're going to see that in about 10 slides away. Now, let's think about the stoichiometry of the thermochemical equation, because whenever we have the balanced chemical equation, there will be always a stoichiometry that is involved. If you look at this example, we try to decompose water into the hydrogen and oxygen. We understand the the heat now is a positive 572 kilojoules. Let's think about this reaction. We are about to decompose water. In this sense, water is a system we want to study. And of course, product becomes to a surroundings maybe. Since we're going to focus on the water, do we think decomposition of water will occur automatically? Of course not. Why? Because if the water decomposes itself automatically, there won't be any drop of water in this world. So that makes so much sense that there's something else is required in order to have the reaction going forward. What is this something? Energy. Water requires to absorb, because remember that's a plus 572, that's an endothermic reaction, right? It's endothermic, means the reaction have to get that amount of energy in order to have reaction going. One way to think about it, we can consider the amount of heat or the heat of the reaction as the reactant. Because without that reactant, reaction is not going to take forward, going forward. Just like, remember we talked about the limiting reactant. If the limiting reactant is gone, one of the reactants gone, reaction stops. So heat actually can be considered as a reactant. If there is enough amount of heat, reaction will not perform the way we expect. Since we put the limiting reactant concept on this energy, apparently, so we can write up the stoichiometry for this thermochemical equation. From the balanced chemical equation, we recognize that we can do the molar relation between the different substances. So compound A, compound B can be connect throughout the moles. With the stoichiometry, molar ratio as the conversion factor. But what is even more about this thermochemical equation is heat becomes part of the equation, part of stoichiometry. So we add the heat as the fourth component of the stoichiometry. In this way, we can convert most of substance into the heat. Gain or loss, it depends on the sign we calculate. So how can we do the conversion in this way? We have a moles of substance to the kilojoules. So when we deal with the stoichiometry of any thermochemical equation, remember, we always treat the heat of a reaction as one of the reactant when we establish stoichiometry. Why one of the reactants for heat? Because heat, as we mentioned before, could be the limiting reactant. Without enough amount of heat to put it in the reaction as a reactant, this reaction may not perform the way we expected. That's a limiting reactant. This type of problem has been experienced when I was in college. So here, as many of you guys are not in the chemistry major, so I'm not going to put this too much on you guys, but I just want you guys to realize delta H could be part of stoichiometry. At least this is what I expect you by learning stoichiometry of a thermochemical equation. Speaking of heat as a part of stoichiometry, now we realize we add heat that's between the moles. Moles to moles of different substances can be directly connected throughout or using a balanced chemical equation. And also, we can go moles to the heat to the moles if we have to. But usually, we consider heat is one of the terminal of this solution map if we want to design it, because usually if we have a thermochemical equation going on, people will ask how much heat is released, how much heat is absorbed by the reaction. So once we put the heat into this solution map here, and we find out things can become more and more complicated and more interesting. So for example, if I start with the grams of a substance A, we can go through the moles, then get to the heat. If you have a heat that's known, so we can start from the heat. Let me use a different color. So we can start with this heat and go through the moles and get to the grams or volume of the solution if we have to. So by introducing heat as a part of stoichiometry, we just expand the stoichiometry to the very new level. Now let's take a look at an example about the stoichiometry on thermochemical equation. We have an equation. So liquid hydrogen peroxide H2O2 releases oxygen gas on decomposition and also with this amount of heat exchanged. Remember, when I say heat exchanged, I do not indicate the direction of the heat. So exchange can be considered as a neutral word. In order to answer such a question, say how much heat is exchanged, we have to put a sign in front of the value to let people understand, okay, so if it's negative, so that means from the system perspective, system loses energy, right? Now let's look at this question. So there are two questions actually. How much heat is released when 136 grams of H2O2 decomposes? Second, how much in grams of O2 produces when 1.18 times 10 to the 4th kilojoules of heat is released? So here, I'm going to use the template that we prepared for chapter 4, stoichiometry limiting reactant. The same template for this question, because I just want to show you, if you follow the procedures we lay out in a template that we tried in our lecture, we can solve any stoichiometrical question, even some of the problem that is not in chapter 4. But what is unique about stoichiometry in this chapter is, remember, we have this. We consider delta H of the reaction as no reactant. We just simply put the delta H in the position of a reactant before we even start thinking about stoichiometry. All right, so what are we going to do here is we're going to follow the template that we used in chapter 4. In our first step, we collect information. When we look at question A, there's only one piece of information that we need to collect, 136 grams of H2O2. So we put it in place. The question wants to know how much heat is released. It doesn't say anything about the units of this energy. All we can do is just pick whatever the unit of energy we want. Remember, the most common unit for energy in this chapter is kilojoules, so we just choose kilojoules. When we look at this thermochemical equation, we realize that both H2O2 and heat are reactants. By the way, is this a limiting reactant problem? I hope you say no. Why? Because we know the amount of one reactant. Question asks us to figure out the amount of second reactant. So when known, it is not two of the reactants that we know the amount of. Therefore, we realize this is not a limiting reactant problem. Okay, let's go to the second step. We collect conversion factors. First, we write up the balanced chemical equation. Now, in this chapter, I want you guys to put heat in the position of the reactant like this. So this is the amount of heat that we put in as a reactant. Now, we write up the stoichiometry. Starting from 2H2O. 2H2O means 2 moles of H2O2. Our second term is another reactant, which is negative 196.1 kilojoules. And if we jump over to the product side, 2H2O, meaning 2 moles of water, O2, meaning 1 mole of O2. That is the pool for conversion factors we collected from stoichiometry. And of course, I have some sense that this is a conversion factor that we are about to use in this question because it has H2O2 and kilojoules. These are two things that's been mentioned from the step 1. The second part of the step 2 is to collect the molar mass. Do we have to collect the molar mass? Remember, question gives us 136 grams of H2O2, so grams of H2O2 is given. We calculate the molar mass of H2O2. We find out it is 34.02 grams, so we write it up into the equation form of conversion factor. 34.02 grams of H2O2 equals to 1 mole of H2O2. And I believe that is pretty much it for us to collect the conversion factors. As we move on to the chapter 3, we need to answer, are entity given and entity desired the same? No, of course it's not. Because question gives us H2O2 wants energy, kilojoules. Two very different units, meaning two different entities. Since it's two different entities, we understand that it's a stoichiometry question. Since it's a stoichiometry question, remember, so here we have H2O2. We start with the grams of H2O2 right here. So how we're gonna select the solution map? Remember, question wants heat in kilojoules. Solution map must be grams to moles of H2O2, then to the heat. This is exactly the solution map that we're going to pick for question A. So again, keep that handout handy, because with that handout, we can solve any stoichiometrical problem in Chem 1 class. Alright, so this is our solution map we have just discussed, from gram of H2O2 to moles of H2O2 to kilojoules of the heat. As we carry out the calculation, so this is what we have. We find out it's 392 kilojoules. Negative 392 kilojoules. So in order to answer this question, so we say negative 392 kilojoules is released. Doesn't sound right, does it? Remember, when we say the energy is released, what sign does it indicate? Of course, it's negative. Reaction is exothermic reaction. Heat coming out, the system loses energy, so the heat of delta H is negative. As questions already determines the direction of the heat, do we have to put a negative sign in front of energy? Of course not. So the correct answer is positive 392 kilojoules for us to report. Again, I want you guys to understand why the negative sign is gone. Because the negative sign is being taken care of by the word like released. Negative sign means heat coming out. Heat coming out is released. Since questions has already predict the direction which is turned out to be correct, we do not have to put a negative sign in front of a value. So we simply report 392 kilojoules. So some people may say, what happened if I pick a negative 392 kilojoules? That means you are not going to get any credit if such questions is in the multiple choice question. It's either 392 or positive 392. If you choose negative 392, no credit whatsoever. So I would really want you guys to pay special attention about the sign of the energy we are going to pick. Check the question, read the question carefully. Try to figure out what the directionality of the energy flow indicated by this question before we pick the value. Before we can make such a decision whether we have to include a sign of the energy or not. All right, now let's look at the second question. How much in grams of O2 produces when 1.18 times 10 to the 4th kilojoules of heat is released? All right, first step, collect the information. We only have one piece of information, kilojoules, that amount of kilojoules. So we reported 1.18 times 10 to the 4th kilojoules. Sorry, I forgot kilojoules as a unit in this slide. Well, if you think about it, there's something else needs to be done. Congratulations, because you are getting it. What is that something else needs to be done? Sign of the energy, because question says this amount of energy is released. What does that mean? It means we need to put a negative sign in front of the energy. We do not pick 1.18 times 10 to the 4th. We write it down as a negative 1.18 times 10 to the 4th kilojoules. Sorry that I forgot to put the kilojoules right here. Okay. All right. Look ugly, but you understand what I'm trying to do. Question wants us to solve for the grams of oxygen, so we put the grams of O2 in there. And I'm not quite sure which one's reactant, which one's the product at this moment, because I need to know what the chemical reaction is or what is the thermochemical equation of this one is. By checking out this reaction, I find out heat is in the reactant, O2 is a product. What does that indicate? Stoichiometry. Limiting reactant? No, of course not, because we only know the amount of one reactant. From this balanced chemical equation, we can easily get the stoichiometry out of it. Negative 196.1 kilojoules equals to 1 mole of oxygen. And also we need to collect the molar mass molar mass of oxygen, because grams for oxygen is what the question wants. Molar mass of our O2 is 32.00 grams per mole. We write this into the equation format with entity attached. As we move on to step 3, we understand that this is a stoichiometry question. As for solution map, we have kilojoules of the heat. Heat is a part of stoichiometry, so that amount of heat should be to be converted to the moles of oxygen. Question was grams, right? So we just put the grams at the end. According to this solution map, we can start off the calculation. And then, as you can see, why we put a negative sign in front of it, because negative sign cancel. You can wind up a positive grams of O2. So let me say this one more time. Read the question carefully about the directionality of heat, because sometimes we need to add a negative sign in front of it. Sometimes we need to remove negative sign when we report heat. Okay, so extremely careful about reporting values of the heat or energy. The last major topic of this chapter is Hess's law. And this is very bizarre. 3 S's altogether, Hess's law. Hess's law is not one, the most confusing topic of this chapter. If you do not understand how it works, people usually have a huge problem understanding the calculation behind this Hess's law. And I have to say, calculation for Hess's law constitutes, I'm not going to say half of this calculation problem, but at least I would say 30 to 40%. So this is how much weight of this Hess's law in this chapter in terms of a calculation. So I want you guys to listen carefully, okay? Think thoroughly, follow my discussion, okay? Ask me question if necessary through the email, or if you want to call the conference. I think I can do it. Okay? And I'm probably going to send out an email to let you know that, okay, how the conference can be held once I get through how to get this thing set up. We start off discussion of Hess's law by checking out the heat of sublimation. Heat of sublimation, according to the definition, is the enthalpy change of sublimating 1 mole of a solid directly to vapor. And of course, we have delta H sub of sub L as the symbol to represent heat of sublimation. Here we're going to use water as an example. We are going to sublime or sublimate 1 mole of ice into 1 mole of vapor. Okay, so 1. As you probably recognize, this is not even chemistry. Okay, it is a physical chain. Remember, we're talking about thermodynamics. That is the field of physics. So this is an energy diagram. All right, so from solid to the vapor, and we got arrow going up. When arrow going up, what does that indicate? Is this a exothermic reaction or endothermic? Delta H of sublimation, positive or negative? Remember, final state is gas state, right? So energy of vapor minus energy of solid. Greater value minus less value. Delta H of sublimation is positive. Reaction is, you got it, endothermic reaction. Well, let's take a look at it how we can figure out the delta H of this sublimation without doing any experiment. As you may recall, for a substance, there are three states, right? We have solid, we have gas, which is a vapor in this case, and then there's one more, liquid. So I'm going to add a liquid. Liquid has to be in the middle of it, right? Because solid goes to liquid, liquid goes to vapor. So liquid must be in the middle of it. In order to heat up a solid into the liquid, we understand there is a heat of fusion to melt down 1 mole of water. And in order to convert 1 mole of liquid water into 1 mole of gaseous water, such process is called vaporization. We just happen to have the heat of vaporization for water. So by inserting water right in the middle of it, we split this one process into 2 steps. Reaction 1, reaction 2. Now, how do we think about this heat of sublimation? What I'd like to remind you here is, regardless of what kind of a delta H we're talking about here, there are delta H anyway, right? Since there are delta H anyway, they all are state functions. Why is that so important? Because since they are all state functions, they have nothing to do with the path system chooses or we choose. They are only the function, or they are the function only depends on the state that we give them. So if you look at the delta H of sublimation, that's from solid to the vapor. And there are 2 delta H's that involve the liquid, from solid to liquid, from liquid to vapor. In other words, delta H of sublimation actually is these 2 delta H's combined, as indicated in this diagram, obviously. And of course, as we already discussed, this delta H of sublimation is endothermic because delta H is greater than 0. This discussion, by having delta H of sublimation split into the 2 delta H's, is what we call Hess's law. So Hess's law is about how we can split one overall process into the various steps. Once we make it work, like make it from solid to the vapor, all we have to do is to add up delta H of each individual steps. This is what the Hess's law tells us. Delta H of an overall process is sum of delta H of each individual step. Delta H is state function, and of course we have a lot more other state functions. State functions like energy, volume, pressure. S is something that we're going to talk about in Chem 2 class. Its name is entropy. Temperature is also a state function. How do I know them? As a state function, they are capitalized, right? Remember, if you have a symbol in uppercase, such function is a state function. So let me put it the other way. Hess's law suits for all state functions, not just for enthalpy. All right. The reaction, as an example we used here, is the physical change. For physical change, we can usually to have this energy diagram laid out nice and easy for us to figure out just how the Hess's law works. Imagine that we have a reaction that we cannot make such diagram, energy diagram. So we put something right in the middle and make it nice and easy. Is there any other way for us to figure out the delta H of an overall process? One thing for us to go here or to figure it out is, let's look at our conclusion. Delta H of sublimation equals to delta H of fusion plus delta H of vaporization. Where do we find these two delta H's? These two reactions. Does that necessarily mean if I have to add these two delta H's together, and since this two delta H comes from the two reactions, does that necessarily mean that we need to add these two reactions together? Let's try it out. It doesn't hurt for us to try, right? So let's add these two reactions together. So we add solid water, liquid water. They both are the reactants from this reaction, these two reactions. So they both are the reactants. And we got the liquid water as a product and the liquid water as a gaseous water as a product. Put them on the side of our products for the addition. And we realize there's something that we can do about this overall reaction, right? We see liquid water on both sides. So say we subtract liquid water on both sides. So these two cancel. What do we end up here? Solid water, gaseous water, gaseous water. What do we get here? We get our target equation. Is that a coincidence? I'm afraid not. So this kind of analysis leads us to think about there could be another approach for us to use the Hess's law using chemical reactions. If we find out the overall reaction is a sum of the two-step reactions, all we have to do is to add the delta H of these step reactions together to have the delta H of the overall process or overall reaction. This is our approach to solve chemical problems with Hess. So one of the applications of Hess's law is to answer the question with the multiple step equations. In order for us to get it, we have to go through certain steps of manipulation. Our goal here is to manipulate those step equations so that we can get the target equation back. I'd like to introduce my own approach. This approach cannot be seen anywhere in the textbook in this country. Before we do the manipulation, I'd like to introduce a concept called non-recurring substance. For each every step equation, we need to highlight non-recurring substance. What is non-recurrent substance? Non-recurrent substance must come from the target equation. Has to. We cannot pick substances from anywhere else. It has to come from target equation. And those substances must show themselves only once in the entire step equations. If we got a two-step equations, show only once in both step equations, in all step equations. If we have three, all step equations. Only once. These are some substances we want to pick. Why do we want to pick the substances like this? Because imagine yourself driving on a highway. Say you want to go from Palm Bay up to Vieira. Now that, if you realize, we got a 3-mile post in Vieira. So we cannot just say, okay, so which mile post? Say in Vieira, right? Because Vieira appears 3 times in the mile post. It is not unique. So what do we have to do? Just simply tell people which mile post or which exit in the city of Vieira that we have to take. It's 188, 191, or 193. All 3 exits are the Vieiras. So we have to find something unique to let the people to know which exit we have to take in the city of Vieira. Same thing here. We have to find something unique. So we can use this as a reference for us to manipulate those step equations in order to get the target equation. So finding non-recurring substance is the big piece for us to deal with this kind of calculation problem. So here I'm not going to just talk those procedures line by line, because we can use those procedures in our next example. So in this problem, we try to solve delta H of this reaction in making carbon monoxide from carbon and oxygen. Direct measurement of this reaction is next to impossible. We have a very slim chance to get it done. The reason for that is when we burn our carbon with oxygen, at the very beginning, we're going to get a carbon dioxide anyway. So we have to find a different way to figure out the heat of the reaction for this one, because simply direct the measurement using calorimetry or calorimeter doesn't work. What we can think of here are the 2-step reactions. We burn carbon in oxygen in order to have carbon dioxide, or we can burn carbon monoxide in oxygen to get carbon dioxide. Both can be done. As a matter of fact, the heat of the reaction of these both reactions have been reported. For step 1, it's negative 393.5 kilojoules. For step 2, it is negative 556 kilojoules. Now, with these 2-step reactions, can we figure out the heat of the reaction of our target one? Let's go through those steps. Remember, our first step is to find the non-recurring substances. Non-recurring substance must come from target equation. So that means we only have 3 to choose from. Okay, no more, no less. And what we're going to do here is to check out these 3 substances against the step reactions and find out which one that shows only once in entire step reactions or step equations. We start off carbon. How many times do we see carbon in these step equations? Once, right? Because I do not see carbon as a free element anywhere in reaction 2. Therefore, I'm going to give it a different color. So I'm going to put a yellow color. So I highlight carbon as a non-recurrent substance because carbon shows up only in reaction 1, not in reaction 2. So it is non-recurring. It doesn't appear itself in other place. What about oxygen? Oxygen here is another non-recurring substance. Oh, it has color already. So we highlight the carbon in green color to let people understand carbon, elemental carbon, is a non-recurring substance. Speaking of our second substance in our target equation, oxygen, we realize oxygen is not a non-recurring substance. It is a recurring. How do we know it? Because we see oxygen in both step equations. Now, let's check out the third one, carbon monoxide. Do we see carbon monoxide in the first reaction? So let's see, carbon, oxygen, CO2, carbon dioxide. We do not see carbon monoxide in reaction 1, but we do see carbon monoxide in the reaction 2 here. So carbon monoxide is another non-recurring substance. And I also would like to remind you, we figure out the 2 non-recurring substances, one for each step reaction. It's usually happen in this way. We can pick at least 1 non-recurring substances for each step reaction. And we're going to use that as a reference to tell us how we are going to manipulate every step reaction. People may wonder what happened to the carbon dioxide, because carbon dioxide here is a product for both step reactions. Remember, non-recurring substance must come from target reaction. Do we see carbon dioxide anywhere in my target equation? Of course not, so I don't care. I don't care this carbon dioxide, because I believe when I'm done with this Hess's law, carbon dioxide will disappear. Or to be true, it will cancel each other themselves out. Okay, so do not worry, carbon dioxide. Okay, that also showed up in the step reaction. We only pick something from the target equation as a reference to help us understand how we manipulate each step reaction. Such reference is called non-recurring substance. Once we figure out 1 non-recurring substance for each step reaction, now let's look at step 2. It says all non-recurring reactants shown in the target equation must appear on the left when manipulating step reaction. What does that mean? It means when we look at the target equation, non-recurrent substance carbon is the reactant. in my target equation. That means carbon must be on the left in my reaction 1. If it is not, we need to do something about it. Obviously, in reaction 1, carbon is on the left, so reaction 1 is good in terms of a position of elementary carbon. What about the reaction 2? Reaction 2, the non-recurrent substance is carbon monoxide. As it turned out, carbon monoxide is a product in my target reaction. That means carbon monoxide has to show up on the other side, on the right-hand side of the step 2 reaction. Right. So carbon monoxide and oxygen must go to here. So what are we going to do? We're going to move carbon monoxide and oxygen to the right. Meanwhile, we take carbon dioxide to the other side. This is exactly when we said we try to reverse the reaction, right? So we will reverse this combination reaction to the decomposition reaction. This is exactly what we're going to do. So we realize that we have to reverse our second step reaction in order to make sure carbon monoxide is on the correct side of this equation. All right, so once we realize what we're going to manipulate the step reactions, and as we figure out how we manipulate step reactions, we're going to step 3 to make the mathematics. To make mathematics out of this manipulation. So say if we wanted to reverse the equation to switch non-recurring substance to the other side of the step equation, we reverse the sign of delta H. Remember, we need to reverse reaction 2 in order to keep carbon monoxide on the right-hand side as a product. If you want to reverse the reaction, remember we have to change the sign, right? So we multiply -1 to delta H of this reaction 2. So this is how we change the sign. And we do the same on the reaction, so we multiply -1 to the reaction 2 this way. So we understand we reverse the step reaction. Okay. There's another non-recurrent substance showing in the step 1, right? In the reaction 1, carbon. And we find out the carbon are on the same side. But in my step reaction, the coefficient of carbon is 1. The coefficient required in my target equation is 2. So what are we going to do about it? We need to multiply this first reaction by number of 2. Why? Because we want to make 2 carbon in order to match the number of carbon in my targeting reaction. Remember, if we wanted to make a coefficient of a carbon from 1 to 2, we multiply it. If we want to multiply it, we multiply the entire reaction or equation. So we multiply the first reaction by 2, meaning we multiply delta H of this reaction 1 by 2. Now, let's see. I'm going to use orange color. When we check the non-recurrent substance for step reaction 1, we got 2 carbon. So that's 2 carbon right here. Same coefficient, same side. After manipulation for the reaction 2, we have 2 carbon monoxide right here. And we have 2 carbon monoxide there. Same side with exactly the same coefficient. That means perfect. So next step is we're going to add these two newly manipulated step reactions together. 2 times reaction 1 plus -1 times reaction 2. Since we're going to add up these two reactions together, we're going to add reactants all together. So this is a reactant from newly manipulated reaction 2. These are the 2 reactants from newly manipulated reaction 1. We add them all together, we got the 3 reactants. Same thing here. We got the 2 carbon monoxide, 1 O2 as a product from newly manipulated reaction 2, and 2 carbon dioxide from a newly manipulated reaction 1. We wound up with the 3 products. You see the magic? CO2 cancel out itself. And also, we can subtract O2 on both sides. In this way, O2 from the left cancel, and we reduce coefficient 2 of O2 down to 1. This is what we have. 2 carbon plus O2 yields 2 carbon monoxide. Look at our target equation. We got it. 2 carbon, 1 O2 yield 2 carbon monoxide. So by checking out adding these 2 manipulated step reactions together to see whether we wind up with our target equation, we know for sure whether our manipulation is correct. In this example, we find out it is correct. Since it is correct, we follow exactly the same manipulation for the delta H's. So we twice the amount of delta H of the first reaction, as is shown up right here, plus we change the sign of the delta H of the second reaction, put them all together, negative 231 kilojoules. Okay, this is how we perform Hess's law with the multiple step reactions. There are a lot of wording, a lot of processes, steps that we have to follow. And if we want to do this problem by following those procedures, it's going to take us a lot of time to do it. So here, I'd like to give you guys a slightly different approach. Same thought, but we deal with the steps slightly differently. Same reaction, because I want you guys to look at this and compare that to the one we have just discussed. And I hope you would like this approach. All right, so same question here. Remember, our first step is to find out the non-recurring substance. What we need is we find at least one non-recurring substance for each step reaction. Remember, non-recurring substance must come from our targeted reaction. So we call it carbon, oxygen, CO. Those are the 3 substances we get from the target reaction. Are any one of these non-recurring substance? Remember, non-recurring substance means it shows up only once in all step reactions. Check out carbon. Carbon shows up only once in step reaction 1. We do not see elemental carbon in second reaction. So we say yes for carbon. Carbon is a non-recurring substance for reaction 1. What about O2? I see O2 in both step reactions, so it doesn't qualify as non-recurring substance. CO. How many times do I see CO in both of step reactions? only once in reaction 2 because I do not see CO anywhere in the reaction 1. So I'm going to make a carbon monoxide as non-recurring substance for second reaction. Remember, this is exactly what we did in those procedures that we explained before. Now, remember, there's still a lot of wording going on here. I try to replace it with a table. By the way, carbon dioxide shouldn't be included or not even considered for non-recurring substance because it doesn't appear in my target equation. Okay, so what I'm going to do here is to use those non-recurring substances from each step reaction, and all we have to do is ask 2 questions for each step reaction. Do we need to reverse this reaction? Do we need to multiply this reaction in order to have a correct coefficient? Why do we have to reverse the reaction? Because we want this non-recurring substance on the correct side in the target equation. All right, so let's start with the carbon. Right. So when we look at the carbon here, do we need reverse this reaction 1? No. No, we don't, because carbon is already on the correct side. The math for us to reverse the reaction is we multiply this reaction by -1. So -1 times. So that is the operation, mathematical operation for the reverse. Do we need to multiply this carbon in order to have the correct coefficient? Yes, we do. So we're going to multiply the first reaction by 2 in order to make up 2 carbon for the targeted reaction. Now, let's look at the second reaction. Remember, our second reaction has carbon monoxide as the non-recurring substance. I got 2 carbon monoxide on the left in reaction 2, 2 carbon monoxide on the right in my target reaction. Definitely we need to reverse. Do we need to multiply the second reaction in order to have correct coefficients? No. So the dash means no operation whatsoever. All right, this is all we need because we just figure out how we are going to manipulate every step reactions. For first step reaction, all we have to do is multiply first reaction by 2. For second reaction, what we're going to do is we're going to multiply the second reaction by -1. So this is the operation that we're going to do, and we're going to do exactly the same with those values, delta H's. 2 times delta H of the reaction 1 plus -1 times delta H of reaction 2. Do we see the same value? Yes, -231 kilojoules. I hope you like this approach, because this approach, okay, so we do not have to go through all this wording by simply setting up the table with the reverse or multiplying, try to answering those 2 questions. We will know just how we're going to manipulate those step reactions. And that definitely saves us a lot of time. Okay, so here, I'm going to speed up this process, try to demonstrate to you that we can get this problem done, say, within 30 seconds. Okay. So, because as you can see, this question is in a multiple choice question. And if you got it wrong, there will be no credit. So it's a very challenge for us to know how to get this problem done in a very short period of time. All right, so if I'm the one to take this question first, like I already do, so I'm going to find out non-recurring substance. So BaCO3, how many times do I see BaCO3? So see once in these two-step reactions, so it's non-recurrent substance. All right, BaO, once, it's a yes, and CO2, yes. So I do not have to worry about the rest of the species in this target, so in the step reactions, because they're not in target reaction. All right, now I need to find out, okay, so this non-recurrent substance in which reaction? CaCO3, reaction 2. BaO, reaction 1. CO2, reaction 2. Now to find out that we are having two non-recurrent substances for one particular reaction, all you have to do is to pick one. So I'm going to pick BaCO3, barium carbon monoxide, to do the business. All right, so according to this table, so let's check out BaO, because this is non-recurrent substance, right? So non-recurrent substance for reaction 1. So my BaO is on the right with a coefficient of 2. Where's my BaO in target reaction? Same side. Reverse? No. And what are we going to do with this coefficient? Multiply by 1/2 to get rid of the 2. For second reaction, BaCO3 is the non-recurrent substance. We see BaO. Okay, so that's the wrong side, right? BaO should be on the left, so we need to reverse it. Do we have to multiply anything? No. All right, so for first reaction, we multiply it by 1/2. For second reaction, we change the sign of delta H. So this is exactly what we're going to do. So that's positive 269 kilojoules per mole. Of course, I spent probably 1 more minute trying to explain why I'm doing this, but I just hope you guys can exercise it to see whether you can get it done within, say, 30 seconds. It should be. All right, so this is the Hess's law dealing with the multiple step of reactions. There is another application of Hess's law. We talk about the second application of Hess's law. First, I'd like to introduce you a new concept called standard enthalpy change. Everybody understand what enthalpy change is. What about standard? Standard comes from a standard state. As a matter of fact, there are a lot of standard states. So for example, if we have a gas, that must be 1 atm. What the atm is, we're going to talk about this in chapter 10. For the aqueous solution, it must be 1 molar and 1 molar only. For pure substance, it must be the most stable form at this particular condition, 1 atm and 25 degrees Celsius. Let me give you an example. Both diamond and graphite are made of elementary carbon. Which one's more stable? Graphite. So we pick graphite for setting up the standard state of carbon. Why the standard states? Because throughout the years, we have collected a whole lot of delta H's. So the reaction that got the most benefit out of this standard state is the formation reaction. So what is formation reaction? Formation reaction means that 1 mole of substance forms from its stable element. As for standard heat of formation, we have to add in the standard state. F subscript stands for formation. 0 superscript stands for standard state. So for standard heat of formation, we call delta H 0F. Here, we're going to use the standard formation of water as an example to show just how we understand this formation reaction. I just want you guys to realize standard heat of formation is just 1 mole. one molar substance forms, right? Since it's said forms, so it has to be the product. So we put a 1 in front of the water. Then we determine the coefficients of the rest. Apparently, we realize formation reaction is a form of a combination reaction with one particular condition. Coefficient of a product must be 1. Second, how are we going to deal with those free elements? In their most stable forms, every free element have 0 as their standard heat of formations. Period. No argument. This is how we set up the standard. So just like if we talk about how tall the Everest is, so we said it's almost 8,900 meters. From where? From sea level. Why can't we go down to the bottom of the sea? So that depends how we choose the standard. So that is same reason how we choose a standard. We choose a standard for every free element with the most stable form as a 0 for their standard heat of formation. So whatever the value that we got from this formation reaction actually is the formation heat for such compound. Plus sign means such formation reaction absorbs energy. Negative sign means such formation reaction, in theory, should be the exothermic reaction. Of course, the more negative the delta H0F, the more stable the substance is. As it's turned out, the water is a lot more stable than any other of these two free elements. So that's why we do not have a hydrogen. We have a certain amount of oxygen, but we have a whole lot of water. Throughout the years, more than 150 years, we have collected a bunch of delta H's, as I already spoke. And we can play the games. So we can play the games so that we can have a delta H0F for many, many compounds. And we call it as a standard heat of formation for such compounds. Why is they're so useful? Because we can use this to predict how the renewal reaction that we are going to perform. How does it look like? What kind of a safety precaution that we're going to use, right? Or we're going to predict. So, for example, this is a reaction in order to prepare highly pure TiO2. Remember, TiO2 is the reactant to make the high pure titanium metal that we can use for stealth fighter, so on and so forth, in our defense industry. One of the major concerns for us to think about this reaction in order to design it is whether this reaction is exothermic or endothermic. If a reaction is exothermic, we have to design a vessel that absorbs heat, right? Because the reaction releases heat. So we have to design a reaction that absorbs heat. So that means we need a circulation of cold water, for example. If a reaction is endothermic, the design should include some heat source to provide heat to make the reaction to take place. That is why, for us as a chemist, before we start off the reaction, we check out the delta H0F for this reaction to understand just what kind of reaction we are looking for, especially whether this reaction needs heat or needs to be something that's we get it cool down the reaction. So what is the approach if we have this reaction as an example? First step, we break each every reactant into the elements using their negative delta H0F. How does it work? We start off TiCl4. We're going to split the TiCl4 into the elements. Remember, it cannot be Cl. It must be Cl2 because Cl2 is a lot more stable than atomic chlorine. The reaction yields 1 titanium and 2 chlorine. So what? What is interesting is if we reverse the reaction, we realize this is the formation reaction because the coefficient of titanium is what? 1. If the coefficient of titanium 4 chloride is 1, for the formation, we can use the delta H0 of this titanium 4 chloride. But that is for formation. The actual reaction is the reverse of this formation reaction. Now we understand that we can simply add a negative sign in front of it. What happened to the 1 plus? Because the coefficient of titanium 4 chloride is 1. So we're going to multiply the negative of delta H0 of titanium 4 chloride by 1. So now we understand where this negative sign comes from, because the reaction is reversed. We're going to do the same with 2 molecules of water. 2 molecules of water actually comes from this reaction. We simply multiply the reaction in the bracket by 2. So 1 mole of water decomposes into half moles of oxygen and 1 mole of hydrogen. If we compare that with the formation reaction for water, we realize the reaction in the bracket actually is the reverse of this formation reaction. Formation reaction of water, we can actually find out what the delta H0F for water is. Since the reaction is reversed and multiplied by 2, so that's 2 times negative delta H0F of water. Are we done? Yes. We just simply break every reactant into their elemental forms through the decomposition. Why the negative? Because we realize here's negative sign, here's negative sign. So we use the negative of standard heat formation of this reactant to break up this reactant into the elements. Alright, so we got the elements in a higher level, energy level. What's our next step? Our next step here is to form products with the elements. So for example, titanium now bonds with oxygen in order to form 1 mole of titanium oxide. So that is the standard heat formation of titanium 4 oxide, TiO2. Remember, question is going to form 4 moles of HCl. So that is why we need 4 multiplied by the standard heat formation of HCl, because for a standard formation reaction, the coefficient of HCl is 1. So it's going to have 4 times of standard heat formation of HCl in order to make the product. In this way, from the element go all the way down to the products. Remember, the heat of a reaction is final minus initial, right? And this is the overall process. They got 2 steps. All you have to do is add up those delta H's all together. I put the red, those represent the products. The one in blue represent the reactants. This is how it works according to Hess's law. Because Hess's law says the delta H of an overall process is a sum of delta H of each individual step. If we want to make it a general, So this is the general form of the Hass's law when we use delta H0F. So remember, sum of delta H of each individual step. So first step, we break up the reactants into the element, then we form products with those elements. According to mathematics, if we have a negative in every term, remember, this is a sum of multiple products. So that M is subject to change. For example, if we have two products, so that's coefficient is 1 for TiO2, 4 for HCl. The N represent the coefficients of each reactant, different reactant. 1 for TiCl4, 2 for H2O. According to the math, we realize if it's in the second term, we got negative sign in there, we can extract the negative sign out. Why do we want to extract negative sign out? Because that makes more sense in chemistry. Remember, delta H0, F, that's for product. Product is relabeled as final state. Reactant is what we labeled as initial state. Delta means what? Delta means final minus initial. So we do not have to worry about whether I should change the sign of a delta H0F anymore, because all I have to do is add up a delta HF for each product. I'm going to add up delta H0F for each reactant, and I do the subtraction. Product minus the reactant. So I do not have to worry about which one should take negative sign in front of it. So that makes sense a lot simplified. Now let's look at our last example. Here, question wants us to figure out the standard heat formation delta H0F of a methanol. It has this formula CH3OH. And equations are given. Apparently, this equation is a combustion reaction because we got a substance burned in air, burned in oxygen. So the standard heat of a combustion is given for this reaction. And also we are given delta H0F of the two other substances. What's the approach? Every time when we see delta H0F, we know for sure it is the second application of Hass's law. We call for this equation. Remember, delta H0F of products, if we have two, we're going to have two delta H0. If we have two reactants, we should have two delta H0F for each reactant, right? In order to make this equation work. What we're going to do is we organize information around that equation. Delta H0 of combustion, we copy it down. Standard heat formation of carbon dioxide, we copy it down. Standard heat formation of H2O, we copy it down. What does the question want? The question wants us to figure out standard heat formation of CH3OH. All right. So what are we going to do here is to break these two terms with our equation. We got the two products. Carbon dioxide has coefficient of 1, so that is why 1 times standard heat formation of carbon dioxide plus coefficient of water is 2, so that's why we got a 2 here multiplied by standard heat formation of water as product. So these are the products. Minus standard heat formation adding up from the reactant. I got a 1 methanol. So that's one here. 2/3, so I'm sorry, 3/2 of O2, 3/2 of standard heat formation of oxygen. All right, now let's see what we know. Because this is a reaction, so standard heat of a reaction is right here, and it's also a combustion reaction, so that means that these two delta H0 is equal to the same. We have so the delta H0 of combustion. Do we know standard heat formation of carbon dioxide? Yes. Do we have standard heat formation of water? Yes. Do we have standard heat formation of carbon? So the methanol? No, but that is what the question wants. All right, now we're hitting wall with this because we do not have standard heat formation of O2 given. We must know this in order to figure out the one with the question mark. Is there any way for us to figure out the value of delta H0 F of oxygen? I'd like to remind you here, O2 is a free element. Yes. We can assume without any question as for 0 kilojoules per mole for standard heat formation of a free element like oxygen. If you see this type of question later on anywhere in our homework assignment or in our exam, you can assume delta H0 F of this free element as a 0, unless you are told otherwise. All right, so now we have this is delta H0 F of oxygen checked. So we have 1, 2, 3, 4, 5 variables with 4 known. This equation should work. Okay. So we plug those numbers in, and we solve for delta H0 of the methanol, which is negative 238.6 kilojoules per mole. That is for chapter 5. Chapter 5, in my view, is probably new to many of you guys. A lot of concepts has been introduced and discussed, and we talk about something that's totally new. Okay? So that requires a lot of attention for you guys to grasp those new stuff. Speaking of a calculation problem, as far as I can think of, sine of Q and W in order to figure out what the delta E is. Heat equation, Q equals C times M times delta T. Okay, what are we going to do with delta T is something that I want you guys to pay good attention with. Another type of calculation problem I can think of in top of my head is stoichiometry, right? So when we deal with the stoichiometry, remember we include delta H of a reaction as a part of stoichiometry as the reactant. Then we just follow whatever that we have learned from chapter 4 to deal with this kind of calculation problem. The last major type of calculation problem, as far as I can think of, is Hess's law. As you can see, there are 2 major types of calculation problems. I can guarantee you, in every exam that you're going to have, these 2 calculations will be tested. So there's no easy way out for Hess's law. We must understand it because these 2 types of calculation constitutes almost 40% of our credit. Okay. Oh, without the 40% of all the calculation problem in chapter 5. So get on to it, learn it slowly. If you have any questions, I'll be more than happy to answer you anytime. anyway, because right now we all stay at home, so at home. Good luck, and I see you guys in chapter 10.